So my name is Daniel Lim. I'm a third year PhD student in mechanical engineering department under Professor Grace Gu. So yeah, I'm really interested in data-driven mechanical design overall. It's a very new field, but it really has a lot of value, which I will present with using the slides after. But yeah, the projects that I'm working on right now is basically, you know how as a designer or engineers, what we have done before is building a system based on our experience or intuition.
Yes.
And that sometimes works really well. However, problem of that is it requires a lot of time and cost, and sometimes even people's life, right? So what we have found is that there's very rapid growth in three large fields, which is first is a computer simulation, which can simulate what could happen using our design without even testing it. And the second part is machine learning. So what machine learning is really good at is given the data, it can actually represent what kind of structure might perform the best according to our purpose. And the last part is additive manufacturing, 3D printing, which is super exciting that I'm super excited about. So in the past, even though we come up with like brilliant design, it was actually impossible to be fabricated because of the very complex structure. But now we could actually potentially fabricate even in the industry field using metal additive and manufacturing. So that's where I'm at right now. And all of my research aligns with those fields, such as machine learning, not machine learning, but just overall data-driven mechanical design. So as I said in the brief introduction, so data-driven mechanical design, it's pretty interesting, but it sounds like a lot of buzzword. So you might question, does it really work? Or why are we talking about this at this point? So as I said, if you are say like an airplane engineer, what we have done is basically after the Wright brothers invented airplane, we basically did with trial and error method. So as an engineer, we just draw out from the intuition or experience that it might work. Sometimes it does work. However, most of the time it doesn't. We know it as an engineer, right? So problem of this is that it costs so much money and time and even people's life. So as I said, three very exciting area that's developing right now is computer simulation, machine learning, and 3D printing, which enables all these things possible with fast iteration. I hope, Stephen, can you go to the next slide?
Yeah, that's fine. I think he was adjusting.
All right, sounds good. Thank you. So we are basically living in a very exciting era, express evolution of design. So next slide, please. Yeah, so yeah, it might sound before example one. Yeah, so I'd like to give a very specific example of how this could be implemented in the research. Could you go to the previous slide?
If you can go back one slide.
Yes. So this is very interesting work that has been done by my colleagues. It's actually like a previous literature that I'm working together. Is that, I don't know if you're familiar with lattice structure, but lattice structure is basically very porous structure that is architectured that can perform stronger than any type of foam material. So it's specifically designed to perform well in the strength and lightweight. So when you see, even though it looks very similar, the left geometries, there are three geometries. So one on the left is one with very primitive shapes. So beam structure is regular cylinder. And the middle one is what human designers have found. So they basically just controlled a little bit of the curvature of the beam. And then they thought that they found, hey, this is the optimal design that can perform well. Like it's strong and lightweight, so it can perform better than anything else. But what was really interesting is that after running all the simulation and let the machine learning come up with the optimized design, we have found that even like it's 2 times stronger than the original shape and even 17 times stronger than what human designers have thought that they have found the optimal design. And we not only the simulation will be empirically validated that this actually works. So one graph that you want to see on the right, the blue one is the model that we created using 3D printing. And the red one and black one is the representation of human optimization and also primitive shape. Yeah, you can ask us any question. I mean, you can ask me any questions if you come up with any like.
It's the 3D printing. One fashion when it applies to industry or what is what is the state of that in terms of costs of 3D printing?
Very, very good point. So even now, cost and even time required to manufacture those print parts is a big bottleneck for the 3D printing. But thanks to development, so right now literature are really focusing on can we reduce the time and cost required for fabricating this type of technology. And I'd say we might need 5 to 10 years more to actually be widely used in the vastly used in the industry. But for example, Adidas, the shoe company, they made a sole that could be fabricated within just an hour that performs better than any other like cushion soles. And they were able to actually sell it very well because of the fast fabrication process. So I won't say it's like a best solution that can beat injection molding, which is almost impossible at this point, but it will definitely replace some of the parts that really requires like customized parts with better performance.
Yeah, so over time it may become more commonly used. Based on cost, price factors and stuff. Yeah.
Exactly. Same with computer. Like computer, it was really expensive and large that people didn't expect that this will be all personal and like using as a laptop. I think that like 3D printing might go with a very similar way.
Yes, yes.
I have a question. In your diagram, you have ML driven. Is
Yes.
actually not just ML, but shall we say human augmented, right?
The middle one is human augmented, but the right one is actually what's proposed from the model that we developed.
Okay, that means there is no human, only driven by the ML and the data that you saw, and not augmented in the sense that the human doesn't play a role in the decision.
We gave a guideline, but most of the design proposed is, as you said, it was driven purely by the ML machine learning.
Where do you get lattice information data? Because I think for ML, data is very important. So just curious in this case, where you source the data to build this?
Yeah, so very good question. Actually, I'm surprised that you guys already understand the depth, in depth about this research, is that the data is the control point of the curve of the beam. So what we did is using computer simulation, we actually created 20,000 different geometry, and we did compression tests in the computer simulation, not actual one.
Oh.
So with that being said, each simulation might take around 1 to 2 minutes to see like what kind of performance it has, but it can, the point is that it can very fastly prove what kind of design performs at the action, and that we can predict the outcome using the simulation.
Oh, so you used computer to generate the data, essentially.
Exactly.
Oh, it's
that's a beauty. Because
yeah, that's very interesting. So you could, okay, because for instance, for self-driving, you use physical data that's outside.
Yes.
In this case, you can actually generate the data and then to feed it into ML to make the decision. Okay.
Exactly. That's like a really good part of what we can use. Because empirical study is really useful, but sometimes it's very time consuming and resource intensive.
Yes.
Yeah.
Very good.
Yeah, thank
Only
you.
on slide 2. So
yeah, I'll try to speed up. Next slide, please. Yeah, so now we think that can this be implemented to the industry, for example? And not just 3D printing, but this is actually the research that I'm doing with Lam Research, which is a semiconductor equipment fabrication company.
You know that.
Oh yeah, great. So Lam Research had an idea. I mean, we proposed an idea that there's a apparatus called faceplate that's used in the semiconductor device fabrication. And what it does, it pours gas to the silicon wafer, to make the wafer. However, the problem of conventional design is that they actually made these holes into very regular pattern, uniform pattern. Problem is that, as you can see from the left figure, it's actually in the pattern. But if the gas flows into a very small channel and then at some point, if it just like spreads it wide, the problem is that the gas is actually not very uniform. So what we did here is we actually hypothesized, can we optimize this structure to have better uniformity of the gas? And the answer was, after implementing the machine learning method in this geometry design, we were able to achieve, even though it's still numerical results, but we were able to achieve 8.7% uniformity increase in the gas flow.
Oh, wow.
So yeah, so it was super surprising, because you know how they really focus on like improving 1% of the output performance of the wafer, but there are, like, from this example, I was really confident that, hey, this is something that industry need right now. Because yeah, human cannot go over all the details of the design, and even making this and testing it just requires too much resource.
Yeah, this has immediate application for
Exactly.
research, right? Yeah.
Yes.
Yeah, very good. Very good.
Yeah. So next slide is, yeah. So now we are at the point of like, what project am I proposing to Heart to Humanity? Is the project titled ARMS, which is Air Drag Reducing Microstructure Surface. Next slide. Yeah, so it's basically one of my project in 3 large themes on data-driven design. So my previous work and what I'm currently doing is about stealth technology. So that's what I have done. And 2 things that I'm working on right now is, one is a fluid systems. For example, the semiconductor research is one of the good example of fluid systems, data-driven fluid systems. And the other one is bioscaffold, which I'm right now just looking at literatures on how I can evolve more on that. But today I'd like to focus on the fluid-based system. Next slide. Yeah, so as the picture suggests, a lot of gas pipelines, especially in US. So gas pipelines is actually a really good method, energy efficient method to transport all the energy to the nation. But the problem is that each point, they require compression station. And the reason is because in order for high pressure gas to move along the nation, it actually requires very high pressure to be given as an input. But the problem of it is that if it travels at a certain point, you need to increase the pressure again using the compressor. And the biggest reason that the pressure reduction happens is because of the friction between the pipeline and the gas. So what I propose is, next slide. So even 30 years before, people already found that shark skin, very uniquely designed shark skin, is actually reduce the friction between fluid and the surface. So I was thinking of my idea on this project is to implement this idea, this concept of microstructure to the internal part of the pipe so that we can reduce the fuel, increase the fuel efficiency used to transport gas from the gas station. Next slide.
One quick question.
Yes.
Looking at the ARMS pipe, the first thing I think about is people have tried, in ARMS, they tried rifling. Like in guns, they try to do rifling to increase the output fast. So, but you also straight line.
Yes. So those are 2 different methods, but as Mr. Kwan said, it's very important method for the bullet to travel faster and wider and more, it gives more stability basically.
Yeah.
But here, the pipeline, it's a straight line. But what it does is actually, it kind of prevents the vortices from happening. So a bit different mechanism, but very similar application, I say. So yes, my answer is that it is straight line, but it can, using machine learning, like optimization, the geometry optimization, it could be spiral line. And we honestly do not know that yet. But there is a very good chance of that being the solution too.
But doing that, does it actually eliminate the repumping or still require repumping?
Reduce probably.
Yeah, reduce the energy required for pumping.
Reduce
Yeah,
the
we
energy.
still need those, but
You still need pumping.
exactly, because I expect the friction drag reduction of the friction will be around 5%. So it doesn't like sounds like a lot, but it really does save a lot of energy because it's passive. So we don't need to actively implement something. It's just the structure itself.
Mhm.
Yeah. So yeah, my core concept here is I want to explore how we can optimize this ribboleth structure and also fabricate this pipeline internally. So problem of the literature that is missing right now, people have actually worked a lot on implementing this on the airfoil, for example, to reduce the friction drag of the airplane. But the problem is that they haven't done much empirical work, experimental work on the internal pipe, circular pipe. And the reason is that with conventional method, it's just impossible to fabricate it. Like how would you pattern the structure internally? So my solution to this is now as an empirical wise, I'd like to implement 3D printing. So next slide. So 3D printing, as it's like really free of manufacturing constraints, I have done the research after like these are all research outcomes after March. So I used this preliminary outcome as I used the 3D printer to create this little tentacle structure. And then now I'm at the stage of creating this experimental setup to see if there's like a really effect of basic structures such as this triangle or blade structure that has been suggested in the literature. So that's where the point I am right now. And I'm trying to advance this using machine learning to actually optimize this ribboleth structure to create the best performing drag reduction pipe. Yeah, so that was the introduction. And the last slide would be, so my goal for this ARMS project is to develop a microstructure pipe system that can reduce over 5% of the friction reduction. So, and my quantifiable goal is just have a 1 peer-reviewed journal and patent submission by end of 2022.